Okay, we will start the seminar now. So good afternoon, everyone. Welcome to a new episode of our series academic journal organized by SmartMat. SmartMat is a newly launched open access academic journal. It's co-launched by Tianjin University and widely published last year, aiming at a broad spectrum of intelligent material research. The founding editor and editor-in-chief are Professor Hu Wenping from Tianjin University and Professor Zhang Hua from City University of Hong Kong. So my name is He Qiyuan, and I'm from the Department of Material Science and Engineering at City University of Hong Kong, and I will be your host today. So today we have pleasure and honor to actually have two speakers for two seminars this afternoon. And we'll have Professor Li Lianzhong from Department of Mechanical Engineering in Hong Kong University, and Professor Huang Haitao from Hong Kong Polytechnic University. So the title of the talk of the first speaker, Professor Li Lianzhong, is 2D layered materials for electronics. Professor Li is currently the chair professor in nanomaterial for future electronics and the chair professor of physics by courtesy in University of Hong Kong. He obtained his bachelor and master degree in National Taiwan University and a PhD degree from University of Oxford. He has been working as a senior faculty member in COST and the University of New South Wales, as well as a director for cooperative research in TSMC, a major semicon company. He is a highly cited scholar since 2018 and an advisory board member in Universal Scientific Education and Research Networks and a top 1% scientist in 2017. Among many prestigious rewards, he is the winner of the Hubert Research Fellowship for experienced research in Germany. So now, without further ado, let's welcome Professor Li to give us the talk. Let me stop.
Okay.
Professor
Li,
you
thank you very
share
much.
your screen now.
Okay, let me share my screen. It's working. Okay, thank you very much. Okay, yeah. So it's my great pleasure to be able to share what we have been doing in the past few years, and really happy to have a chance to deliver a talk online. Okay, so today my topic is on 2D layer materials for electronics, and I'm from Hong Kong University. And result presented today were actually collaborated with colleague at TSMC and KAUST. But the slide represents only my personal opinions. It doesn't represent any opinion from others, okay? And the outline today, I'm going to talk about the trends in device technologies. Then we can discuss further scaling with 2D materials. Then we will talk about 3D monolithic integration. Okay, so about the device trend in recent developments, so we can see three very obvious trends. The first one is the scaling, meaning that we try to shrink the size of the devices, and the scaling still continues. And the second trend is system optimization becomes very important. And third trend is new material actually start to be involved in the future development. Okay, let me further explain more. Let's see. Okay, yeah. So let me start from the very basic for those who are not really in electronics. So for a planar silicon transistor, the scaling means that we try to shrink down the size of the devices, meaning that the source drain distance becomes shorter. So this actually brings a very good benefits. The first one actually they increase the on currents. Okay, so for example, if you look at left-hand side bottom the graph, so we shrink the size, we mean scaling actually on current increase, which is needed for future electronics, because on current represents the computation speeds. We can simply say that. And however, if the source drain distance becomes shorter and shorter, maybe down to a few tens nanometers, so the source drain, because of the distance become very short, the source drain leakage become very pronounced. So what actually happened is, as shown on the right-hand side bottom, the off-current basically increases. And this phenomenon becomes very pronounced, particularly when we actually talk about the device gate length, the channel length, maybe shorter than 20 nanometers. That's what's happening so far. So the scaling, although scaling brings good benefits, we have a higher speed, but it actually lose the gate control, meaning that it's difficult to have low power devices because actually we are losing power. And also the computation become more difficult because of the off current. We need basically enough on and off current ratio, right? So that's basic problem. Okay, so I mentioned that the scaling actually still continues. So, but we probably need to actually mention a little bit on the technology node. We often read the news from the newspaper. So we talk about N3, N22, N28, N2. So what I mean N2, it doesn't mean the channel length is 2 nanometers. So the physical gate length is actually shown in the bottom. So for N28, the gate length is about similar, about 30 nanometers. But for N22 down to N3, particularly for N3, the gate length is only it's about 14 nanometers, which is much larger than the terminologies. There is a historical reason why people do that. People actually, the company actually talk about the technology node shrinking by looking at the performance rather than the gate lengths. So there is an apparent difference, a discrepancy between gate length and technology node. Okay, so you can also see that the gate length becomes very difficult to shrink. Even people claim that the technology node already very, very small. Okay, what industry people did actually is trying to change the geometry of the structures. For example, the left-hand side shows planar structures. So where you have the top gate, so basic top gate control the on and off of the channel. And when actually it further shrink down to 22 nanometers, some of the companies start to use so-called FinFET structures. They where the silicon planar silicon actually become flip. So by doing so, there is a benefit that you can actually deposit the gate metal surrounding the fin structures, meaning that basically you have a three-way control. So left-hand side, right-hand side, top side, you have a three-side. Actually, the gate metal actually can enforce the electric field to control the carrier density within the channel. So this is a very clever way. It's called FinFET. But however, the FinFET actually continued to N3, and it becomes very challenging because N3, the physical gate length is about 14 nanometer. The quantum transport become pronounced, meaning that the source drain tunneling becomes very pronounced, and even you use FinFET structure, you still cannot really control to suppress the off current. So therefore, we need very aggressive, even more aggressive approach. So there is a IBM actually recently demonstrates so-called gate all-around structures. So basically, they flip the silicon sheets actually horizontal again, and by doing so, you have you can deposit metal surrounding the nano sheets. Then you have all direction control of the channel. So that's the way actually people actually shrink the size of the transistor. Okay. Then what happened is that gate around. So based on the calculation and also the conclusion from the researchers, people normally believe that this is even use gate all around structures, the gate length cannot be really further shrink. So particularly when we talk about the N1 technologies, the gate length should be smaller than 10 nanometer on the right-hand side. So gate all around still cannot provide sufficient gate control. So there's a other possibility. You can try to use new materials, for example, 2D materials with the thickness about 1 nanometer, or carbon nanotube with the thickness also 1 nanometers. The thinner thickness actually allows the gate electric field more easy to penetrate to the channel materials. So therefore, very thin material, ultra thin material down to 1 nanometer should provide the new chances for future electronics if people really want to shrink, want to push the technology node to N1. So let me explain a little bit more why not silicon for N1. Because gate, as we mentioned, gate all around structure cannot offer enough gate control for silicon. So another thing is that if we want to make gate all around structure sufficient and more efficient, we need to actually thin down the silicon. So currently we can see that silicon thickness, probably people can actually push down to 5 nanometer. And if we want to push even thinner, it's become very challenging. So due to the process difficulty, silicon is a 3-dimensional material. So it's difficult to really make it a thing as 2D materials because the whole surface is difficult to control. So even the silicon can be made thinner. So the mobility should be very low. This is due to the surface scattering. The reason is the same because the silicon is 3D materials. So 3D materials definitely has the unfinished bonding, so which actually form the dangling bond or bond to another surface like a dielectrics. So those surface bonding actually perform as a charge scatters. So basically that will actually suppress the mobility of the silicon. Okay, so we can see this phenomenon very obviously, very clearly on the left-hand side graph. So it shows the electron mobility versus channel thickness. The green line basically shows how the silicon mobility decrease was the channel thickness decreasing. So, but if you see the tungsten selenide, molybdenum sulfide, WSE2, those are three typical transition metal dichalcogenide. They still maintain very good mobility, which is higher than silicon when the thickness down to 1 nanometer. So this is the reason 2D materials stand at a great chance for future electronics. So I summarize a little bit here. Why 2D materials stand at a great chance? Because it has high quality film, which can be grown in a wafer scale. This is the part I'm going to focus in my talk later. And due to the nature of the chemical bonding, so it is actually free of surface scattering. So it's a high mobility. That's the reason they have a reasonably high mobility. And the thickness is about 1 nanometer thick. So therefore, it's a naturally very good for gate control, particularly for N1 technology. Okay, so the second trend we observed actually is the optimization. And so I'm taking this graph as an example. So people normally need to consider power performance costs in addition to the scaling of silicon chips. So the case is probably for the old generation people like me. Actually, you still remember in your computer we have the memory DRAM, which is very far away from the CPU. So this is called DIMM technologies. They have very limited bandwidth because the communication between CPU, one CPU calculate, they have a result, they need to send to the memory DRAM side. So need to go through this bus, IO bus. So very limited wire actually connecting. So therefore the communication bandwidth is very limited. And recently the company actually, semiconductor company, start to work on so-called advanced packaging. So the middle graph basically show that they actually put DRAM and the CPU core on the same substrate and just adjacent to each other. So the distance is much shorter compared with DIMM technologies. And this is called 2.5 generation advanced packaging. Apparently the power consumption and bandwidth actually increase, power consumption decreases. So even aggressively, the company basically start to work on 3D integration, 3D advanced packaging. So the way they do is actually they put the DRAM directly on top of the coil, the CPU core, and then put very dense through silicon via and to connect DRAM and core. So these actually 3D should be much better than 2.5D because of the via, the wiring actually much shorter compared with 2.5D. Okay, so those are actually aggressively researched, and also the company are actually aggressively working on the approaches. And for academic researchers, so we should look into even further. So what are the future? So I think this nobody will have objection that monolithic integration could be the next step. So so this slide actually shows the example of the monolithic integration. So the left-hand side scheme basically show that if you have a high-speed transistor like a silicon CMOS actually underneath for the first layer, so basically you can integrate, you can deposit or transfer the second layer transistor, or you can transfer material and then fabricate the second layer transistor. You can actually integrate the backend of line compatible transistor on top. Actually, and this drastically increase the transistor density because you directly add in the second layer transistor. And then even on that, I mean, even more, actually you can put in-memory switch. You can put a memristor on top of the transistor if they actually meets very well to the backend of light process. On top of that, you can also put the sensing units and power gating. And if you have a low temperature compatible process, so basically, you actually save a lot of footprint from underneath, right? So for the conventional silicon, and all these components probably you need to lie down the same plane. Therefore, they occupy a lot of footprint. And if we have a technology which allow you to do the monolithic integration, then you can build like a high-rise building. So the chips, the semiconductor chip becomes a high-rise building. You can put a lot of functionality just on a very small footprint. So this is the idea for monolithic integration. And this is not a new concept. A lot of university researchers have done this work and tried to do the research for many, many years. But it's very apparent that the low temperature compatible process, or I would say transferable materials, are really needed. Okay, it's because it's very difficult to build the second layer silicon on top of first layer silicon, simply because of the temperature is too high. You cannot really build so many layers. So the thermal budget actually doesn't allow, the silicon doesn't allow really that high thermal budget to do that. Okay, so monolithic integration is another obvious trend for future electronics. Okay, so the second point, let me draw your attention to how to do the whether 2D material has a chance for N1 scaling. So I'll discuss this from three perspectives. The first one is material selection. The second one is how to do the growth. And the third one is actually device contact. So let me very quickly go through this slide. So there are so many 2D materials, more than 1,000 2D materials based on the simulation. So we cannot really extend one by one by experiments. So therefore, doing simulation, and first we do the very simple screening and find out those potential candidates, and then further do the simulation to screen out and basically select few possible candidates. And this is what actually we were actually doing. So for example, we can select the material like 40 different material which are basically relatively stable in air. So for in semiconductor company, probably people they don't really want to do those very aggressive materials which easily reacted with oxygen. So those are not really preferable because the process window will be very narrow and difficult to do the fabrication. So we select about 40 different materials relatively stable in air, and then try to do the simulation. The simulation is quite straightforward. We put the materials actually in the scheme on the left-hand side. So that's the 2D material in between top gate and bottom gate. Because the material is very thin, so we don't need to consider the gate all around structures. We just have a top gate and a bottom gate, and then the gate control should be sufficient enough, very close to gate all around. And so the gate length, we set it as about 7 nanometer, which is very aggressive for N1 shrinkage. So then, and for different material, they have their own mobility, which can be found in simulation, right? This is a phonon scattering mobilities, which can be found from literature, and effective mass, which can be obtained by DFT calculation of the band structures. So with those two parameters, we can actually calculate how much current you can get from those devices as shown on the left-hand side. So the color contour plot on the right-hand side, the color code represent the current density. So obviously you can see platinum selenide, indium selenide, and tin selenide, they are very outstanding. However, those materials are not really mature in terms of the growth, and it's very difficult to find good quality one in markets. So therefore, we pull back a little bit. We use tungsten sulfide and tungsten selenide as a N channel and P channel respectively. And MOS2 roughly is okay. So because MOS2 has been studied for quite a long time, so it will be a good starting point to understand those how those 2D material perform. Okay, so that's the way actually to do the preliminary screening. Okay, So of course, when we talk about growth, we need to understand how to do the chemical reaction. So back to 2012, we published a paper on how to grow single crystal monolayer MOS2 flex. The reaction is very straightforward. We use molybdenum oxygen powder as a precursor together with the sulfur powder. So we evaporate those two powder by different temperature. We control at different temperature. When they evaporate, they react in air, and then they can precipitate on the right-hand side, the downstream side. If you set a correct temperature on the right substrate, they can form monolayer triangle lattice, which is single crystal MOS2 flex. And so if we grow those materials on different substrate, you can see different alignment. For left-hand side means that the left-hand side graph shows the random orientation. The MOS2 actually orient to different direction because the substrate doesn't really play too much role. Amorphous substrate doesn't really control the orientation. So they just randomly oriented. But if we grow the materials on top of the sulfide substrates, so you can see the triangle actually points to upward or downwards, so 0 degree and 180 degree. So basically, this is called van der Waals epitaxy. So at this time, the underlying sulfide substrate actually try to control the orientation of MOS2 through a van der Waals interaction. But it's kind of an epitaxy process, but only through weak van der Waals forces. And but the issue is that the triangle actually point to 0 degree and 180 degree. They are having the similar or the same energy for this configuration. So therefore, when you grow the materials on sulfide, basically the orientation is 50-50%. So unfortunately, when you actually merge those triangle, you increase the growth time. So those triangle merge, you will find that the grain boundary actually form in between. So that's a problem, because when we talk about the scalable electronics, we always think about single crystal materials and then without grain boundary. So those grain boundary are a very obvious defect, which is scatter the carrier. So if your transistor actually just land on this grain boundary side, then your electrical devices, the performance will be largely impacted. So this is something we don't really want to see. So how to control to get single crystal? Let me take hexagon bore nitride as an example, and then we can move to the MOS2 later. So hexagon bore nitride is a atomic layer insulators, and it is very interesting because it is also a 2D materials, meaning that the surface is free of defect. So which is very useful actually to isolate the 2D materials, 2D channel transistor, 2D transistor or 2D channel with those 3D materials. Because when we talk about 2D transistor, we always need to put 2D layer on top of something, right? So that's because we are living in a 3-dimensional world, so we have to use 3D materials to host 2D. So those 3D materials, of course, they have the surface dangling bond, as we mentioned just a few minutes ago. So those dangling bond, basically, they would deteriorate the mobility of 2D. So there's a better way actually to avoid the charge scattering or reduce the charge scattering rate. That is, you can put a 2D materials, 2D insulator in between. Then they can isolate the hexagon bore nitride can isolate the 2D and also those surface charge from 3D materials. Although hexagon bore nitride is not really high K materials, but the thickness of bore nitride is quite thin. So therefore, the contribution of the hexagon bore nitride to equivalent thickness (EOT) is not really that serious. So that serves as a temporary solution if we cannot find a better way to suppress the charge scatter. Okay. So I won't discuss too much on the benefit of hexagon bore nitride, but the things I like to discuss is that recently we found a way to control the hexagon bore nitride orientation. So the hexagon bore nitride is also the same as MOS2. When it grow, if you have a hexagon bore nitride triangle pointing to opposite direction, like 0 degree and 180 degree, when it merge, they form grain boundary, which is not wanted. So the recent study in our group, basically we found that if we can control the copper 111's substrate to a certain degree, then you can find the hexagonal bone nitride actually they grow and they point to the same direction. So how does it work? So, and this is something we are going to discuss now. So basically we find that on the copper 111, so copper 111, although copper 111 is a single crystal. Yeah, first let me introduce how to prepare a copper 111. So we don't like to use copper foil because in industry we like to use wafer. It's easy and more compatible for the machine we have. So basically we deposit 500 nanometer copper on top of the sulfide C plane substrate. Okay, then we do the annealing, actually hydrogen under hydrogens at certain temperatures. We try to form the copper 111 single crystal, and this can be induced by the underlying sulfide substrate crystallinity. So once you get a single crystal copper 111, so it doesn't mean that the whole surface is flat. So typically you can see those step H shown on the right hand side, the cross section. So those step H is atomically thin. So actually those step H basically plays an important role in guiding the orientation of the triangle. So the left hand side scheme shows that if we don't consider the step H on copper 111, so those two triangles basically they have their random, they have their freedom to point to 0 degree or 180 degree. You have two orientation. However, if you consider the presence of the step H, the step H serve as a docking site. So then they can actually the hexagonal bone nitride seed basically they prefer to attach to the step H first, and then only one configuration is having the lowest energy. So we did our simulations, and the simulation basically came out as very consistent results. Only one configuration is having the lowest energy. Okay, so those energy basically, so one single energies, I would say low energy, basically those configuration is the preferred structures. So if we can control the growth to make the energy difference larger, and then we probably can control all these triangle pointing to the same direction caused by the step H guiding process. So we call it Van der Waals epitaxy process. And these actually reasonably explain how to control to make those say 2D materials as a single crystal. So that has been successfully demonstrated in hexagonal bone nitride growth. So what about MOS2 structures? Okay, so I'm going to show you another interesting example. So my student basically, so this is this was the work done by Dr. Arich at KAUST and together with Professor Vincent Tan. So Arich basically, she tried to grow MOS2 on top of the gallium oxide, beta phase gallium oxide. So the beta phase gallium oxide is very interesting. It has a very obvious step H on the surfaces. It's also single crystal. So when we do the growth of MOS2, we find that most of the, I would say all the triangle basically point to the same direction. And then due to the surface structure differences, the precursor diffusion direction is limited. I mean, along the step H direction, the diffusion rate is faster. So vertical to this step H direction, the diffusion rate is very slow. So therefore, it actually forms the, I'll say, ribbon structures. So all this triangle actually nucleate just right on the step H, okay, because that's the easy way, and then with a lower energy for the seeding. And due to the step H control, all these triangle actually point to the same direction. And also the diffusion control, as we mentioned, they prefer to grow along this step H direction. Therefore, eventually they form an MOS2 nanoribbon. And this is a single crystal and nanoribbon. So this is quite interesting. So the experimental result also is also consistent with what we observed. And this is controlled by step H. And the length of the nanoribbon can be as long as centimeter, and this is quite fascinating. So that is discussed about the microscopic detail. So we try to understand what's going on there. So then we do the STM. So TEM, the cross-section show on the left-hand side top. You can see basically on the left-hand side, on the corner side, actually there is a gallium oxide. The gallium atom actually missing. So therefore, molybdenum atom can easily attach to this vacancy to form the MO and molybdenum oxygen bonding. Okay, so when they form an MO O bonding, they have two options. The first one, the MO actually can attach to the upper side oxygen, as pointed by the mouse precursor. And the other way, on the right-hand side, the MO can actually attach to the bottom oxygen. So these two scenario actually has very different energy. So left-hand side is much lower compared with right-hand side. So therefore, once the MO actually attach to the oxygen, they form the bonding to the upper side oxygen. They actually already control the orientation of the MOS2. On the right-hand side, this is 180 degree, and left-hand side is 0 degree. So basically, what this story tells us is that the orientation of the MOS2 or the 2D material was probably controlled by the initial reaction chemistry. Okay, so the very simple conclusion is that step H provides an active site, which is decisive for orientation control. And this has been proved by the copper 111 growing hexagon bone nitride on copper 111, as well as MOS2 grown on the gallium oxide. And a recent paper by Zhang Yanfeng in Peking University also developed a process, and very interesting process. They successfully demonstrate the growth, wafer scale growth of MOS2 on top of gold 111. So the process is exactly can be exactly explained by the age epitaxial theory. So they try to do the polycrystalline gold on top of a tungsten foil and then do the annealing. Then they force the gold to form gold 111 single crystal and with exposed step H. And when they do the growth of MOS2, and those step H actually control the orientation of MOS2 triangle. And then when you merge all these triangle, they form a single crystal. The whole wafer actually is only one crystal, single crystal MOS2. Okay, so so this is another very strong evidence is that the step H control really works for growing wafer scale 2D materials. Okay, yeah. So let me summarize the status of the TMD growth. So MOS2, for example. So wafer scale single crystal is probably very close to desire for industry. So this has been demonstrated by the Peking University, and also probably another few groups. Actually, they will be having very nice results published very soon. They all demonstrate wafer scale growth of MOS2 on wafer. So this is probably not a big issue anymore. Single crystal wafer size MOS2 is readily available very soon. And the other thing is that high quality, low defect density is totally different story. So because the defect density is not really the same thing as the single crystal growth. Okay, so you can grow single crystal, but if the chemistry is not properly selected, it also results in the film with high defect density, which is not really useful for electronics. So therefore, this is another story. So I believe that CVD sample and it could be as good as exfoliate crystal. So, and this part yet to be demonstrated. And the third part is thin transfer technology. You may already notice that the MOS2 was actually grown on sulfide substrate, and sulfide substrate probably is a not good substrate for silicon electronics, for future electronics, because they are too expensive and also difficult to do the lithography process. So we need to transfer those single crystal or MOS2 film onto the substrate which is suitable for silicon, suitable for microelectronics. So the film transfer technology still needs to be developed. So I think this is another direction which desperately need a lot of research to work. Okay, and then I'm going to talk about the device parts. So for device concern, so metal and 2D contact resistance is very critical. So recently we have shown together with MIT, Jing's group, that if you find a correct metal, find a better metal or a more suitable metal, so the bismuth and MOS2 contact can be pretty good. Although they are not really close to quantum limits, but this is much better. It is already much better compared with all published results in literature. So I would say if you want to reach a low contact resistance metal, low contact resistance for 2D, so my opinion, the very strong metal 2D interaction is needed. So in that case, it's van der Waals contact metal, probably very difficult because you have a van der Waals gap in between, which is a very big barrier for carrier transmission, and unavoidably. So very strong metal 2D interaction, even you have a very strong chemical bonding, that's preferred because you can have a very strong, very large transmission probability. However, if you have very strong metal and 2D interactions, sometimes you end up with another notorious factors, another notorious phenomenon, which is called Fermi level pinning. Then in that case, you cannot control the Schottky barrier high. So the other criteria is that very low Schottky barrier high is crucial. We need to have to fulfill these two criteria in order to have very good metal 2D contact, low contact resistance. And bismuth contact metal is very interesting because it meets both criteria, and because bismuth actually has a stronger interaction with MOS2, because bismuth actually react with sulfur, and which actually provides very strong foundation that you have a very strong, I would say, transmission. The carrier can easily move from bismuth to MOS2. And also the Schottky barrier is extremely low. If you're interested, please go refer to this paper. So I won't go through very detail, but just roughly talk about what's going on. So bismuth is a semi-metal. So they have the, I would say, Dirac-like profile in density of state. So owing to this, I would say, zero, I would say there is a zero density state in the middle parts of the semi-metal bismuth. So those actually align very well to the conduction band. So this is due to the bismuth Fermi energy. It's very close to the conduction band of the MOS2. So therefore, and also the density of states is very unique. So therefore, the Fermi level actually just pin right at the conduction band edge of MOS2, which end up with a very low Schottky barrier, nearly free Schottky barrier high. So that's the main reason why you can see very good contact resistance for such metal. Okay, then let me see. I still have a few minutes. Okay, so let me come to the final parts. I probably just missed a little bit on this one. Let me talk about. I didn't really mention okay. I mentioned about material selection, epitaxial growth, device contact, but I didn't really mention device architecture. For these parts, I mean how to form the MFET or PFET and how to form the CMOS using 2D materials. I think this is still an open question, and because even for the device contact, whether we really want to use top contact as what we show in the bismuth MOS2 contact, or we want to use H contact. So let me show you the H contact. Okay. So this slide basic shows the diagram. On the left-hand side top, so we have a top contact diagram. So basically, metal actually directly deposit on top of the MOS2, and this is a very typical method. People normally use this top contact because of the simplicity. However, for the future electronics depositions, when you consider maybe gate-all-around structures or other more complicated structures, side contact sometimes becomes very useful. So, but side contact, people normally have the issue, have the concern whether the contact between the metal and the edge of the very thin MOS2, whether those very, very thin channel is able to allow enough carrier to flow in. Are we able to get enough high current to operate devices? So basically, actually the Terahons at TSMC published a paper last year in IEDM to discuss about this question. Forgive me, I probably don't want to go through detail, but the conclusion is that the edge contact, sometimes they can perform even better than top contact, maybe comparable or even better in terms of the carrier density, in terms of the current density. So if you're interested, please please refer to this IEDM paper. So the reason is very straightforward, because in this side contact, if you can form the metal which is strongly bonded to the MOS2, the criteria is the same. You need to have a very strong chemical bonding, then you'll be able to have high current flowing through this contact region. So that's the key criteria. Okay, so let me go to the final part. So monolithic integration using low dimensional materials. Initially, I have a lot of example, but due to the time limit, I just want to talk about the simulation parts and how to use low dimensional materials, how the low dimensional material can actually do something useful for monolithic integration. Okay, so then this is the work done by Professor Vita Hu at National Taiwan University. So we worked together before, and so the simulation results actually demonstrate that if we can do monolithic 3D integration using 2D materials as SRAM transistor units, basically if you stack many layers, you can save a lot of power. So in brief, left-hand side, the graph A shows 1 tier back-gate SRAM using 2D materials, just simply by design. And we can see that the 6 transistor form a 1 SRAM unit, 1 strand cell. So 6 transistors actually sitting on the same plane. This is called 1 tier, very typical method. So they occupy certain region like 108 nanometer and 268 nanometer. And then, and I remember this is 7 nanometer technology node. Okay, so if we try to actually to bring this, separate this transistor, 6 transistors into two layers. So we can put 4 transistors in the first tier, the first level, and then put the other 2 transistors on top of the on the second tier. So then by doing so, we have, and then we try to minimize the routing, and then we can come out the area. Basically, we reduce the area a little bit. So from 268 nanometer length and down to 216 nanometers in sizes. It's not really big improvement, but the routing becomes shorter. So it still have the benefits. And then when we come to the 3-tier structures, we actually separate this 6 transistor to 3 level. So of course, we assume that 2D materials can be easily transferred to many layers. You can form transistor easily. That's assumption. So if we can do that, then we can form relatively very small region, and also very neat routing, because you don't need to actually have the routing on the same plane. You can go through the other level actually to have a more efficient routing. So by doing so, you can do the simulation. So if we move from one tier SRAM, 2D FET based SRAM, and move to 3-tier, you can save 44.3% area size. And also you can save the power consumption. So energy delay product, basically you can save about 43.6%, which is quite large benefits. So therefore, this is the benefits. This is why we want to actually use 2D to move the 2D layer from 1 level to 3 level. And this is also, actually this also demonstrates how the monolithic integration can help to push the performance for future electronics. And let me recall the slide I have shown in the past. And the monolithic integration means that you can actually integrate many layers of transistor. You can also integrate those transistor low temperature processable low backend of line compatible transistor or devices on top of the CMOS silicon. So therefore, you can get the benefits of silicon CMOS, high-speed silicon CMOS. Then you can combine with the upper level transistor like a 2D materials, which is aiming at low power consumption. So by doing so, when you need very high power, high speed calculation, you can go down to the silicon CMOS. When you only need very low power transistor, very low power computation, you don't need high power, particularly in the case you don't have enough battery powers, and you actually go back to the go upper level to ask the 2D transistor to perform the calculation. And then you can also put in memories, also memory set on top, and also the power gating or the sensing units. Actually, you can have a lot of functionality just simply by adding all those transferable and also backend of line compatible units or devices on the same wafer using monolithic integration. Okay, so about 45 minutes, good. So let me come to my conclusions. And for the future device trend, scaling continues. System optimization is what people are chasing, and also monolithic integration is also important things, particularly for researchers. And potential N1 technology node, channel materials, 2D transistor metal dichalcogen like MOS2, tungsten sulfide, and tungsten selenide could be quite good choices for the time being. And growth of single crystal 2D material across wafer is possible, and if we can properly adopt the theory of step H epitaxy process. And finally, the monolithic integration is a new playground because they require a lot of new materials and new design and also innovative fabrication process. And finally, I'd like to thank you for being here and online. And I'll pay my special thanks to the people I shown on the slides, and also the collaborators, Vincent Tang from KAUST, Boris Jacobson and Rice, Jing Kong at MIT, Zhang Wenhao at NCTU, Wu Zhiyi, Vita Hu at NTU, and also my previous colleague at TSMC and KAUST. I'll be happy to take questions if you have any. Thank you. Thank you very much.
Okay, that's a really inspiring and a wonderful talk. Thank you for giving us this talk. And our staff are gathering questions from the audience. I think I'll ask one quite simple question first.
Oh, yes, please.
So, Prof. Lee, you are probably one of the few scientists who held a senior position in both industrial and academic. So I will ask you a rather general question. So what is the industrial currently looking at this next generation semiconductors aside from 2D semiconductors? What are other kind of materials people are looking at? What are the opportunities?
Okay, yeah, thank you for your questions. Again, I probably cannot represent company to show any to brief any idea, I would say. But my personal opinion and what I learned from the academic and also industries, there are many different materials which can be used for future electronics. 2D material is only one option. As I mentioned before, you can see that the 2D material is one option because the thickness is about 1 nanometer. So definitely for N1 or below those technology, you need to use very thin channel. So very thin channel, naturally you think about 2D materials and also for 1D carbon nanotubes. So 1D carbon nanotube is also a very excellent choices. So because it has one-dimensional and also very thin diameters. And in terms of the performance, I think 1D channel like CNT should perform much better than 2D. That's for sure. But the challenges are still there for how to integrate carbon nanotube into the large area circuits with controllable density. A particular difficulty actually are in how to control the device to device variation. Let me give very brief discussion. For example, if you want to have a like an N1 technology nanotube, you need to have the nanotubes they are strictly in parallel, and then with the spacing about 3 nanometer for each tube, and each tube is about 1 nanometer in diameters. So it's a very stringent condition how to align those nanotube into they put into in regular manner, and then such that they can have a you can reduce the device to device variation. So from this point of view, 2D material is a lot more easier because you can control just right at the growth age. If you grow highly uniform 2D material, that's easier. However, the problem of 2D material is that the mobility may not be that attractive compared with 1D. So I think probably now there's no definite answer which material would serve better for N1 technologies. But one thing we need to consider, I would like to remind everyone, 1D nanometer is definitely worth doing a lot of researches. But for commercial concern, the technology move very fast. So if those new material cannot move into cannot really chip into, cannot be used, adopted in semiconductor in a reasonably time frames, and then those material will lose their chances because the industry is industry. They're earning money. They're developing technology. They don't care about what material to use as long as they find a way actually to improve the performances. Material probably not the key concern for them. So as a material scientist, particularly for our society here, the audience are all working on material, I believe. So we have to do the researches in the right way and faster to really catch up what industry want to use. That's my personal opinion.
Thank you. That's actually very informative. That's a much bigger question than I thought. Yeah, thank you for the answer. So we do have a few questions from the audience, but due to time limit, we'll pick only a few. Let me see. The first one is actually about the very specific one question. So what do you think about the stability of this TMD growth from CVD method? Generally, are they not good? Yeah, that's the question.
Okay. Yeah, okay. This is a very good question. During the stage, at the stage of, I would say, preliminary proof of concept research, I do not think it is not stable enough. Because when we do the process, we can put the sample in proper condition with a low humidity and proper, I would say, proper environments. Actually, the device can sustain very well for a long time. And however, people do have the concern when you actually pump the devices, pump down the environment, like if you put during your process, you expose your 2D materials in a high vacuum. So those high vacuum probably can actually draw out those sulfur atom, kick out the sulfur atom. So that's possible. So that has been observed by IMEC. So I guess what the stability means that I'm talking about very stringent condition. If you put the high vacuum, put the sample in high vacuum, how many sulfur atoms, maybe certain percentage of sulfur atom will be lost. So that kind of stability, I'm not sure for the moment. So we need to do reliability tests. But if you talk about very general stability, our experience, I don't think it's a big problem for this research at this stage. I hope I have answered the question.
Yeah, thank you for the answer. I think you answered the question pretty well. So we have second question is in terms of pure electronic applications. So is the TMD semiconductors obtained from mechanical exfoliation still better than CVD in most cases? Yeah. Okay.
Yeah, this is also a very, very good question. And yeah, so I think in the past few years, yes, we see a lot of literature data and research paper. Yes, I agree. The exfoliate sample is better. But this situation may be changed soon because the CVD sample has been improved quite a lot significantly, particularly when you change the reaction chemistry, you are able to have comparable quality, at least I would say comparable quality compared with the exfoliate sample, although the paper has not been published yet. But I would say this is, I would say it could be comparable very soon to those exfoliate flakes. So I do not worry too much on that.
Okay, thank you for the answer. So due to time limit, we have one last question. So that is what is the current state of art for graphene transistors, and how does it compare to TMD transistors?
Oh, I see. Okay. Yeah. So this is a tough question for me because I don't work on graphene. So I did have some graphene experience, but I didn't really make it to device level. So I prefer not to answer too much on that. But graphene is not having enough gap. So in terms of high performance digital electronics, probably there's no hope for that, because for digital electronics, you need to have enough bandgap in order to have enough on-off ratio. So even for this gallium arsenide, in long time ago, people normally talk about gallium arsenide. Gallium arsenide is having very high mobility. Why it cannot be used for industry, not replacing silicon? Because it has two narrow bandgaps about 0.65. The number is simply too small. Why? Because when you have very small bandgap materials, your device-to-device variation will be extremely large, which cannot really help, which cannot be used for silicon, for microelectronics. So you can demonstrate one devices, but for industry criteria, it's very different. We always need to think about device-to-device variation. So gallium arsenide, one of the detrimental factors is that the bandgap is simply too small. When you do the fabrication, do the chemistry, do the surface, whatever fabrication process, they actually change the device-to-device variation, very significant, just simply due to the low energy gap. So I think graphene probably fall into the same category. Even you break the gap of graphene, if the graphene gap is still very small, it cannot really serve very nicely for digital electronics. But of course, graphene can do other things like high frequency, maybe. So I'm not the expert in the area. Probably I probably cannot really comment too much on that. Yeah. That's my opinion.
Okay. Yeah, thank you. It's a very good answer. So due to time limit, we'll stop here for the first seminar. And we thank Prof. Lee for this wonderful and very inspiring talk. We hope to see you submit to SmartMat in the future, maybe.
Oh, yeah. Thank you very much. Yeah, thank you very much.
Thank you.